Solve the following system of nonlinear equations graphically. Round your answers to two decimal places. All right, so there's a big hint here telling us that we can round our answers to two decimal places. What that sort of is implying to us is that there's not going to be a single algebraic solution, and because of that, we're going to need to use the calculator to make an approximate solution. All right, now an approximate solution does need to be accurate to a certain number of decimal places, and in this case it needs to be accurate to 2. But I'll show you how to get that in just a moment. Right now, if we want to get an idea of what's going on, here we have two equations. One is the common logarithm of x plus 5. The graph of a logarithm, we're shifted to the right 5 or the left 5 units. So that brings that vertical asymptote back 5 units. And then there's a single point right in front of the asymptote. And since we don't have any changes up or down, that point's just right on the x-axis. The graph approaches the logarithm in this direction, and then it goes out this way. And depending on what the base is, how far it reaches. But I'm not trying to be totally accurate here, just getting a sketch. All right, and then y equals x squared. So y equals x squared, we know that is a parabola, and it's situated at the origin, opening upward, something like this. So what's happening here is there should be two potential solutions, but we're not going to be able to solve for them algebraically because in order to do that, what I would do is, in this case, use substitution. So I'm going to substitute x squared in for y up here, because x squared is equal to y. So if I have x squared equals log of x plus 5, then, well, to solve any equation that has a logarithm, which the argument of that logarithm is a variable, we need to switch into exponential form. Okay, so the base of the exponential equation would be 10 because this is a common logarithm. And the exponent would be this value over here, and that's equal to x plus 5. Okay, but the problem is now we have an exponential equation with a variable in the exponent, and we can't solve that directly. So we'd have to switch to logarithmic form, which would bring us right back here. And we'd sort of end up in this endless loop of which form to use, and ultimately neither can be solved algebraically, at least with techniques that we've established thus far. So, the calculator, let's see how to use that. What we will do is start off plugging in our equations into y1 and y2. So we have log, which is a common log, so use that, x plus 5, and y equals x squared. And I've got a stat plot turned on. I'm going to cancel that, close that out, and I will hit zoom and then come down here to zoom standard to get the standard viewing window. Now, you can see that basically our graph is the same. The logarithmic functions never actually draw very well on screen, so this part does exist. Whoops. This part here does exist going down to the asymptote. They just don't ever get drawn on the screen for arithmetic precision reasons. But you can see how there are certainly two different intersections, just like we've described. So how do we find those? Well, let me make that a little bit larger so everyone can see better. To find the first one, if you'll notice, it looks like it's somewhere between -1 and 0. So I'm going to hit second and calc. And what I'm trying to find is an intersection between two curves. So the curves are y1, which is the logarithmic, and y2, which is the square. And then it asks for an initial guess. So I'm just going to move my cursor somewhere close to where that intersection point is. And it'll do an algorithm and find it from that point. So it comes up with negative 0.79 and 0.62. So one solution is negative 0.79 and 0.62. So it's an x and y coordinate pair. All right, also there's one over here, and in order to get the calculator to find it, we use the same function, second calc, come down here to intersect. The first function is a logarithm, that's fine. Second function is a square, that's no problem. But this time, move the cursor close to where the other intersection is, and it will find that one. So 0.88 and 0.77. Now, there's always a student that will try and use, let's see, let me just hit graph and cancel all that out. All right, so as you move the cursor, you can see it drags along x and y coordinates. And if you get your cursor near that intersection point, well, you're certainly going to get something close to those values, but they're not accurate to 2 decimal places. Even if you use the trace feature, which makes sure your function, as you move, you stay on these functions, it still isn't necessarily going to get close enough to the actual intersection point to be accurate to a certain number of decimals. So I wouldn't rely on those. I would simply make sure to use the second calc feature so that it will run an algorithm to find those intersections for you.